Welcome to Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be taking a look at our last set of notes from the year dealing with neutralizations of acids and bases and also titrations. Now, what happens when an acid is added to a base? Well, this is something we talked about way at the beginning of the year. We got into lab safety, and we talked about when we have acids and bases, we'll always have a weak form of their opposite to neutralize them with to make it safe. So they neutralize each other to form a salt and water. And remember, what we're really looking at is double replacement reactions, one of the reaction types we looked at the very beginning of the semester. Now, in a neutralization reaction, double replacement reaction, we have two compounds. And as a double replacement, what we're really looking at doing is swapping the cations. Remember, cations are the first listed. So the H would be the H plus ion in HCl, and the Na would be the Na plus ion in NaOH. And what we're going to do is swap those two things. Now, good review for the final is remembering in a double replacement reaction, we're making two compounds. And whenever we make compounds, we have to check the charges to find the new formulas of our new compounds. So when we switch that Na and the H, we can't just really write we're going to get NaCl and HOH. We have to check the charges to see what we're really going to get. So to find new formulas, you must check charges and then crisscross reduce. Well, if you take a look at what we have here, we had H plus and OH minus, and we had Na plus and Cl minus coming together, and we crisscross those charge values. So H is a +1, OH minus is a -1, crisscross the ones. Well, that's a 1-to-1 we can't reduce, so our formula is going to be HOH, or H2O. Na is a +1, Cl is a -1, so 1 and 1. So when we crisscross those numbers, we get something that can't reduce, so that's just plain NaCl. And that's exactly what we started with, but remember, you have to double check charges to make sure that is truly what you get for your formulas, because it's not always a +1, -1 situation. And HOH, remember, is really H2O water, and NaCl would be an ionic compound, a salt, the product of an acid-base neutralization. So the ionic compound that is produced in the acid-base neutralization. Now, here is a different acid and base. We have sulfuric acid and calcium hydroxide, but fundamentally it's the same idea. We take the cations and swap them, so that would be the H from the H2SO4 and the Ca from the CaOH2, and trade places. Now notice I said H from the H2SO4. Remember, the ion is H+. There just happen to be two of them because SO4, which is the sulfate anion, is SO4 2-. So we needed two H's to make a neutral compound. So remember, what we're doing is we're putting together the cations and the anions, and we don't worry about how many we had on the left. We have to check charges to figure out new formulas. So H is a +1, OH is a -1, so that's a 1-to-1 when we crisscross reduce. Ca is a 2+, SO4 is a 2-. When we crisscross the 2's and reduce them to 1-to-1, we get CaSO4. Now, the last thing we have to do, and we didn't have to worry about it in the last example because we already had one of everything, is we have to balance the equation. And you'll notice we started with two H's on the left and two hydroxides on the left. So that means on the right side we really need to make two waters to balance it. So all we need to do is add a 2 in front of the H2O, and we end up balancing our equation. So that would be the neutralization of sulfuric acid and calcium hydroxide. Once again, we get water, and we get a salt. In this case, it's not NaCl, it's calcium sulfate, CaSO4. Now, the general process of determining the molarity of an acid or base through the use of an acid-base reaction, or neutralization, is called acid-base titration. And really what we're doing here is we're neutralizing acids and bases in an experimental process where it allows us to determine the concentration of our acid or our base. So we're going to be in a titration using neutralization reactions that we just talked about. Now, the known reactant molarity is used to find the unknown molarity of the other solution. We can't have an unknown acid concentration and an unknown base. One of the two we have to know what the concentration of. And solutions of known molarity that are used in this fashion are called standard solutions. So in our titration, we're either going to have a standardized acid or a standardized base, which basically means a substance of known concentration. Now, in a titration, the molarity of one of the reactants, either the acid or the base, is known. Remember, that's our standard solution, but the other is not known. And that's typically our job in a titration, is to figure out that unknown concentration. Now you know that NaOH and HCl react completely in the following reaction. This was one of the double replacement neutralization reactions we just looked at a second ago. So the acid and the base will neutralize each other to make H2O and NaCl, which is a neutral salt. Now, if I know the concentration of the NaH solution, that would be our standardized solution. Now, in the lab that we're going to end up doing, what is in the burette, the large glass tube that is held on the ring stand, that's going to dispense our known base, our NaOH. So our standardized solution is quite often what we put in the burette. And the unknown solution, in this case in the lab, it's going to end up being vinegar, basically. So we're using dilute acetic acid. We're going to try and find its concentration. Now I know that's probably not what's shown here, but it's the same fundamental idea. Is we're going to have a substance in our flask that we add an indicator to, and then in our burette we're going to have another substance that will neutralize that substance. And our indicator is there to tell us when we're done with the titration. When it goes through a color change, we stop, and now we can measure the volume dispensed from the burette to figure out information. So this is really what we're going to be doing in the lab in a couple of days. So you can use the reaction, the volumes, the acids, and the bases used. We can measure how much acid we put in the flask, and after we're done with titration and stop, we can find out the volume of the base that was dispensed. And we can use that to determine the molarity of the unlabeled acid. In the lab, we're going to be using vinegar. In this situation, we're talking about HCl because it was NaOH being or HCl being neutralized with NaOH. Now, at neutralization, which is called the equivalence point, the moles of H plus are going to equal the moles of OH minus in our titration. So when we hit this magic point at which in the flask we have the same number of moles of H plus as we have moles of OH minus, we are at the equivalence point. And that's why it's called the equivalence. What's equal is the moles of the H plus and the moles of the OH minus in solution. Now, in the actual titration, we refer to this as the end point, the point at which we stop the titration. And if things are set up properly and we're using a proper color change through use of a proper indicator for the typical titration that you're doing, the endpoint is going to equal the equivalence point. Now, how do we find moles? Well, if you remember from our solutions chapter a little while ago, moles equals molarity times the volume. Molarity is moles per liter. If our volume's in liters, liter would cancel and we'll have moles. So what this is really saying is molarity times our volume of the H plus is going to equal the molarity times our volume of the OH minus. And at neutralization, or the equivalence point, then, in a simple titration, now when I say a simple titration, what we're talking about is a simple acid and a simple base. A 1 proton acid, a 1 hydrogen acid, and a 1 hydroxide base is what we usually refer to as a simple titration. And it makes for a very simple application that looks very familiar to what we used before in the dilution equation. The molarity of our acid times the volume of our acid is going to equal the molarity of our base times the volume of our base. Now, for a simple titration, we can leave it at that. But not all acids are single hydrogen acids, and not all bases are single hydroxide bases. We will look at an example of the other, but keep in mind in the lab we have a single hydrogen acid and a single hydroxide base. In the problems that we practice and on the test and on the final, if you're doing a titration, I guarantee it will be a simple titration, and we can think of it as the molarity of the acid times the volume of the acid is going to equal the molarity of the base times the volume of the base for our first year chemistry program here. But the reality is we can deal with more complex situations with this as long as we look at it as not the molarity of the acid, but the molarity of the H plus from the acid and the volume of our acid, and the molarity of the OH minus from our base and the volume of the base. We can deal with, using this equation, if we're careful, really any acid-base titration. But most of the time, we're going to be looking at a single hydrogen, single hydroxide. So the H plus will equal the concentration of the acid, and the concentration of the OH minus will equal the concentration of the base for the ones that we're typically looking at. So here's an example of that kind of situation. What is the molarity of HCl solution if it takes 68 milliliters of 1.2 molar NaOH to neutralize 25 milliliters of the acid? Notice it's a simple acid one hydrogen and a simple base, one hydroxide. This would be our neutralization. And in our neutralization, you can see that it's a simple situation. We have the same mole amount of HCl reacting with NaOH. It's a 1-to-1 mole ratio. Now, technically, to be safe, we really want to look at is not the concentration of the base, but the concentration of the OH minus that comes from the base. But as a simple single hydroxide monobasic base, the concentration of the OH minus is the same as the concentration of the base. It's going to be 1.2 molar. So in our equation, we would have an unknown concentration of our acid times the volume. It said we had 25 milliliters of our HCl, and that would be what's in the flask. We knew our standardized solution was 1.2 molar NaOH, so that's going to be in the burette. And at the end of our titration, we dispensed 68 milliliters. So we have a simple equation where we can solve for X. Now remember, X is going to equal our H plus from the acid, but HCl is a single H plus acid, so it's a monoprotic acid, so the concentration of the H plus equals the concentration of the acid, and we then have determined that the concentration of HCl is 3.3 molar. Now let's look at once where it's not quite that simple. So we're going to look at a diprotic acid reacting with a monobasic base. So what is the concentration of an NaOH solution if it takes 12.4 milliliters of 0.24 molar H2SO4 to neutralize 9.5 milliliters of NaOH. Now we're going to start by looking at our double replacement reaction. Notice when we look at our balanced neutralization reaction here, we ended up using twice as much of the base as the acid, so to speak. It's a 1-to-2 mole ratio between the sulfuric acid and the NaOH, and that's because it's a diprotic acid. And technically, that's something we have to take into account when we're looking at our equation. So if we have H2SO4 concentration being 0.24, and every H2SO4 gives us 2 H pluses, we would double the concentration to get the concentration of the H plus. So now we've taken account for the fact that we are basically using twice as much base as an acid in the situation here. So when we use our equation, it's going to be 0.48 molar times 12.4 milliliters is going to equal X. Now our standard solution was the sulfuric acid, and our unknown was the base, and we had 9.5 milliliters of the base. So if we solve for X, we're solving for the concentration of OH minus, and that was 0.63 molar. But if it is a monobasic base, a 1-hydroxide base like NaOH, the concentration of the OH minus equals the concentration of the NaOH. So we can say the concentration of our unknown base was 0.63 molar. So we can handle, with just a little bit of work, situations where it's not a simple monoprotic acid and monobasic base. But remember, that's not something we're going to do in the lab. It's not something you're going to see in the homework or on the test with this. And that really finishes up our look at titrations and neutralization reactions.